Hi everyone, as I promised, this is another part of the FPGA architectures, and in the slides that I presented before in the first three videos, I basically talked about some of the older technology FPGAs. What I'm going to do today is to talk about the more modern FPGAs. So the basics are the same. It's just that they've added more features and adapted some of the architectural characteristics to match better with modern applications. So I'm going to use this set of slides from Xilinx. I haven't modified them, and I've posted these on Moodle too. So if you need high resolution images, feel free to open it now and look at it as I go through the slides. And of course, I'm only going to go through the first part of these slides, which only talk about the architecture, but this is a very useful set. It talks about the Xilinx tool sets and so on. And the reason I picked Xilinx is because they had these slides. So no preference between Xilinx and Altera. And in the next video, which I'm going to take some of Peter Chung's slides, that talks about both Xilinx and Altera. And Xilinx and Altera is very similar to, so that should not be a problem. Okay, and of course I'm not going to cover everything here, so I'm just going to skip. And go to the slides that I think are useful to look. So sorry, I did want to go through. So basically, this set of slides does talk about logic resources, I/O resources. I'll mostly skip memory and DSP. I'll just show you one or two slides. Same with clocking resources. So if you look at the Xilinx FPGAs, the modern ones. Basically, you have the logic resources, which are grouped into CLBs, similar to what we had before, and you have memories and multipliers. Then they spend a lot of time and effort in adding the I/O blocks that let the FPGA talk to the outside world using faster I/O, and also catering to different serial I/O standards. And also they have global clock buffers. Boundary scan logic is used for programming the FPGA. So if you remember, I showed you the lookup tables and also the switch boxes that an FPGA has, and if you remember, they were controlled by SRAM cells. So your lookup table itself is going to be, if you have a 3 lot, for example, it's going to have 8 memory locations, and you can basically write your truth table in it. So those 8 memory locations could be chained into a linear shift register, and if you shift in the values of the truth table into that, you've basically programmed that logic block. Same goes with the program interconnect. If you remember, your interconnect had muxes, and the control lines of those muxes were controlled by SRAM cells. So add these SRAM cells into the scan chain, and basically that's how you can basically use JTAG or other standards to try to program the FPGA. So this is a Spartan 6 FPGA, and this is from back in 2011. So you know more modern FPGAs came out in the years since. And the important thing that I want you to look at would be the mixture of the type of things that they have here. And you have your regular CLBs, logic blocks. You have your multipliers here. And then you have some specialized blocks like buffer IOs here, or PCI endpoint. So some of the Spartan FPGAs do have hard macros that take care of implementing the PCI Express interface. I mean, if you don't have that, then maybe you can use this much of the area of the FPGA to implement PCI Express interface. It would probably be slower, and it would is taking away a whole lot more resources, or FPGA silicon footprint, compared to providing a hard macro. And this doesn't appear in all Spartan FPGAs. I'll show you in a table in a moment. And then they have the block RAMs. These are the dedicated RAMs, but that's not the only type of memory you can use. You can also program these lookup tables inside these CLBs to act as memory units. And if you do it that way, it's called distributed memory. The hard macro ones are block RAMs. So these are only used for memories. You can't use these to do addition or anything else, any logic, whereas these are malleable and you can basically program them to do whatever you want. Also note that they have a bunch of global buffer clocks, global buffers for the clocks, and they have a bunch of clock management blocks that you can basically define multiple clock domains in your system, and that would work. So Spartan 6, I think I pretty much talked about all of the features. And then they keep dividing FPGAs into families. So basically, they have to look at the cost, performance trade-off. And if you, as a user, as a customer, have a small design, then you want to pay for the cheaper device, which has less capacity and not use all of those fancy features that they have. So this table shows you a flavor of the different types that you have. So these are all Spartan 6. And they share the basics of the architecture, and then you have from LX4 all the way down up to LX150T, and you can see the different features that they have. So in terms of the logic cells, you're going from 15K to 147K here. In terms of block RAMs, you have number of block RAM units, 32, all the way up to 260 something here, and the total block RAM in kilobits is 576 here. It's 4,000 something, right? So basically, in terms of the capacity, they increase, and in terms of the features that they provide. So for example, the PCI Express endpoint block, that's the hard macro that they put. There is no PCI Express as a hard macro here. If you want, you have to tap into the CLBs and use a soft macro to implement PCI Express, but then you have one unit of PCI Express on these high-end devices. So this is pretty common with both Xilinx and Altera FPGAs, that they provide a different set of devices. I'm going to skip these because we've already talked about these, and I'm going to stop at slide number 10. So basically, in the Spartan 6, what they do is they use 25% of them are going to be slice M, 25% is slice L, and 50% is slice X. How did they come up with these 25% and 50%? These are empirical. They ran experiments on many benchmarks, and they mapped them, and they looked at what features are more useful for these, and this is something that caters to the average design that you have. And of course, I mean, they could change in the high-end ones. Maybe you need more slice X. In the low end, maybe you need equal mixture of these. So these are all fair game. FPGA vendors can do all of these games, and these are the features that they have. So your slice M can work as LUT6, 8 registers, carry logic, wide function muxes. If you remember, we did talk about wide functions, and also it can be programmed as distributed RAM. But slice X doesn't allow you to use it for wide function muxes or distributed RAMs. So basically the point that I want you to get here is that the mix of benchmarks that they choose is going to decide the mixture of the architecture. And as I told you before, they can basically combine a bunch of these LUT6s to make LUT7 and LUT8. So if you take the output of these two LUT6 blocks and use this mux, and then the mux select could come from the 7th input, assuming that you're sharing the 6 inputs across these two LUTs, then you would get a 7 LUT. And you can mix the top 7 LUT and the bottom 7 LUT using a mux into an 8 LUT, and that would allow you to implement any function of 8 inputs. And next week, when we look at the flow, what was that? Flow map from Jason Kong's work, you will see that basically it's just the covering. It's just a tree covering question when you want to map, so you don't care what exact Boolean function you're implementing. And also note these 4 flip-flops inside a lookup table. These flip-flops could be implemented as SR latches or flip-flops. Let me skip. Logic implementation we've already done. So this is slide number 14, talks about the fact that you can do latches or flip-flops, and this slide talks about configuring your lookup table as a shift register. So you could take these um, flip-flops that you had and connect them through chains. And if you go back to the CLB, you will see that there are muxes that choose whether the input of the D flip-flop here has to come from the lookup tables or does it come from the mux here. So this is part of the interconnected structure that goes inside your CLB. So it's a very rich routing structure within the CLB, and they can use it to do many different things. So slide 16 shows you, for example, that you can put together a bunch of these and create a 20 cycle, 20-bit shift register. So it's flexible, and hopefully, the synthesis tool is going to take care of all of that. You don't need to manually do stuff. I'm going to skip the I/O stuff. The only slide I'm going to stop would be slide number 19. Just look at how many of these different standards they cover. So basically they have hard macros on the chip that would cater to these different standards, but then again, I mean, you can use the lookup tables to implement any I/O standards that you want. This shows you the flexibilities that you have with implementing the distributed memory. So the distributed memory, remember that this was the one in which you put together a bunch of these lookup tables, a bunch of these CLBs, and configure them to be memory blocks, right? And if you have a single port for read and write, you could do 32 by 2, right? So it's 2 bits wide, 32 words. You could go all the way to 256 by 1 or 64 by 4. And basically, these are the options that you have. So you can basically play with the depth versus width of the memory. And if you want, you could do dual port. So you could have a 2-bit 32 entry dual port, and then you could have simple dual port, quad port, and these are the different options that you can have, and the descriptions of what these are is listed here. Block RAM, this is the one that is dedicated as RAM, and usually these are arranged in a column in the FPGA. So your your block RAM can run at 300 megahertz. You can't do that fast with distributed memory. These are dedicated memory units that they have, and they support up to 2 ports. And you can see the different configurations here. You could do an 18 kilo 18K block RAM, or break it up into 2 independent 9 kilo block RAMs with independent address control. So again, I mean, depending on your application, you could configure it in the mode that is more suitable to you. Slide 28 shows you the DSP block, and later on in Peter Chung's slides I'm going to show you Altero's versions of this. But you have an 18-bit by 18-bit signed multiplier, you have an accumulator, and you have different options of skipping things, or doing multiply accumulate, which is used widely in DSP applications, in filter designs and so on. And that's all I wanted to talk about the DSP. In terms of clock, let me just go to slide 31. By the way, I strongly recommend, suggest that you guys go through all of these slides. The ones that I skipped, I thought were not, as important as the other ones, but going through all of the slides is going to be very useful. Now, the clock sources, the clock could come from the outside pin, so you could connect any oscillators here. They also have a PLL that they can use to provide clocks, and the clocks would go throughout the whole chip. So they have multiple clock domains, which could, go up to 1 GHz for their clock. That doesn't mean that you can run your logic with that clock. It's just that they can provide that clock. All right, let me stop here, and then I'll record another video going over Peter Chung's slides that talk about some issues, but more importantly, towards the end, it talks about power issues.